Hello and welcome everyone to our weekly session titled Latest in Bitcoin Tech, where we go through the weekly Bitcoin Optech newsletter. What is the Optech newsletter? It's basically a weekly amalgamation of the evolutions, the latest evolutions in the world of Bitcoin tech. It encompasses news articles, it encompasses PR reviews, Bitcoin Stack Exchange questions and answers, releases and release candidates, and code and documentation changes. Primarily, it revolves around Bitcoin tech, but also on technologies that are in sync with Bitcoin, such as Lightning Network or Nostr, so on and so forth. So we get together Monday, 8 p.m. Indian Standard Time to go through the Optech newsletter and discuss the news articles, review the PRs, and go through the releases and release candidates and cover off it that we can. We'll do that this week as well. So I will first go through the preface of the newsletter, which gives us a hint into what is to follow. This week's newsletter describes a proposal for speeding up a Bitcoin Core initial block download with a proof of concept implementation that shows a roughly 5x speed up compared to Bitcoin Core's defaults. Also included are our regular sections summarizing a Bitcoin Core PR review club meeting, announcing new releases and release candidates, and describing notable changes to popular Bitcoin infrastructure projects. Right, so that's what we have in store in our gist. We have, I guess, just one news article. Okay, and then we will have the Bitcoin Core PR Review Club. Let's read it first. So the title of the first news article is SwiftSync, speed up for initial block download. Let's read it. Sebastian Falbisona posted to Delving Bitcoin, a sample implementation and performance results for SwiftSync, an idea proposed by Ruben Thompson during a recent Bitcoin Core developers meeting and later posted to the mailing list. As of writing, the most recent results posted in the thread show a 5.28x speed up in initial block download over Bitcoin Core's default IBD settings, which uses assume valid but not assume UTXO, reducing the initial sync time from about 41 hours to about 8 hours. All right, so let's stop here and try and understand the first passage. So this news article basically covers a proposal which is named SwiftSync, right? So what is an initial block download? I mean, all of us have heard the term blockchain, right? So Bitcoin is basically a decentralized distributed ledger where transactions are compiled or arranged in the form of a data structure which is known as a block. And we know that Bitcoin, because it's decentralized, it doesn't have a single point of failure, it doesn't have a single node like the conventional financial networks do, such as the banks, etc. Right? So each individual can spin up their own node and use their own node to validate transactions and use their own node to send and receive payments. And when you do that, there's a process for you to sync up with the active chain tip, right? You have to validate the entire blockchain. You have to validate each and every transaction, each and every script, each and every signature, all unspent transaction outputs. You have to download and validate all of this information, which is like extends computational work, right? And your node bootstraps from scratch, right? So you start from the Genesis block and then you go up to the active chain tip. The active chain tip is the last block that has been successfully mined, right? So if you want to run your own Bitcoin node, you have to uh, familiarize your Bitcoin node with Bitcoin's history all the way from the first transaction that was ever made to the active chain tip. Now, this process of syncing to the blockchain or downloading and validating historical data from Bitcoin's blockchain is referred to as the initial block download or IBD, right? Initial because your node is not in a position to receive. If you connect your node with a wallet, it's not in a position to receive and send transactions because it's not aware which transactions are valid and which transactions are not valid. For your node to be aware that a transaction is valid and thereby accept it or send it, it needs to be aware of the entire history, the transactions history all the way back to the Genesis block, or at least its parent transaction where it was initiated from. So this process is known as the initial block download because you download all the blocks in the blockchain, starting from the Genesis block up till the active chain tip. Now, this is a time-consuming process, and it's becoming more and more computationally extensive, because as time passes, more transactions are made and more blocks are mined, and there is more and more data for you to validate. And it has been observed that technology is not growing at the rate at which the blockchain is growing. And that is why with the computational resources that we have at our disposal, the initial block download is becoming more and more cumbersome. It depends on what your what was the speed of your bandwidth, and what device you are using, what specifications are of your computer on which you're running your node. But if you're running a node on a resource constrained device, then it might even take up to weeks for you to sync up your node to the active chain tip. All right. However, the environment or the bandwidth at which this experiment was performed, and the resources or the specifications of the device that was used to perform this test led to an IBD completion in 41 hours, right? So 41 hours. The experiment that was done by I'm assuming this developer, the IBD was completed in 41 hours using a Bitcoin core node. Okay, so this is has been the talk of the town for quite some time, and people have been coming up with different proposals on how it's possible to make it more and more easy for people to run the nodes, right? Because like Bitcoin is decentralized because people run their own nodes. If people stop running their own nodes, then it's not decentralized anymore. And for that to happen, you want more and more people to run Bitcoin nodes. And for more and more people to run Bitcoin nodes, you have to ensure that running a Bitcoin node is easy, right? Not only is it cost efficient, but also time efficient. Like spinning up a Bitcoin node should be as trivial and as easy as possible. If people have to wait for days or at times even weeks to sync up their Bitcoin node to the active chain tip, then that discourages people from using Bitcoin. And also discourages people from running their own nodes, which leads to centralization, right? So there have been a lot of attempts and efforts being made to ensure that running a Bitcoin node remains very trivial. If some of you might have heard of this proposal known as UTREXO, UTREEXO, that is one proposal that's being talked about. Then there are these two configuration flags, assume valid and assume UTX. So we'll look into these as well because they sync up very well with this news article, and I believe the news article covers them as well. So we'll understand what's assume valid, we'll understand what's assume UTX. So by now, I am assuming that everybody is familiar with what an initial block download is, and what are the hindrances and impediments that one might come across when they are trying to spin up their own Bitcoin node, right? And this proposal in a gist aims to make it easier to sync your Bitcoin node with active chain tip, right? And some of the proposals that have predated this specific proposal, as I mentioned, one of them is Utrecht. So you can go through it. We've covered it in detail in one of the sessions. And then there's assume valid and assume UTXO as well. And both of these we look into. And the new one, the proposal that's been made is SwiftSync, all right? And as per the experiments conducted, then SwiftSync reduces the IBD time by up to 5.28x. So without IBD, Bitcoin Core node took 41 hours to sync to the active chain tip. But with SwiftSync, the keeping everything else adiabatic, it took around 8 hours, right? So that's a reduction of 5.28 times. Before using SwiftSync, someone who has already synced their node to a recent block creates a hints file that indicates which transaction outputs will be in the UTXO set at that block. That is, i.e., which outputs will be unspent. This can be efficiently encoded to a few hundred megabytes for the current UTXO set size. The hints file also indicates what block it was generated at, which we'll call the terminal SwiftSync block. All right. So basically, how this works is that a full node will first download the entire blockchain and validate the entire UTXO set, right? We know that UTXO is an unspent transaction output, and there's a data structure in your node that keeps a track of unspent transactions. So every time you create a new transaction, an old transaction is deleted, it's destroyed, right? And when that happens, that old transaction is removed from your UTXO set, and new transaction is created in your UTXO set. So your UTXO set basically is a data structure in your node that keeps a track of unspent transactions, right? So how this works is that before using SwiftSync, what is to be done? Someone who has already synced their node to a recent block creates a hints file. A file is created, right? Okay, for now we're not using SwiftSync. We have a full node. we have a full node that does not deploy SwiftSync. That full node has been synced to the active chain tip, all right? And what that node does is that it creates a hints file. It creates a hints file. What does that file do? It indicates which transaction outputs will be in the UTXO set at that block. Okay, right. Okay. So what is done is that first we'll take a full node that is in sync with the active chain tip. Okay, and that full node will create a hints file. Now, what is the purpose of this hints file? This hints file will basically have the unspent transaction outputs, right? Meaning the transaction outputs that are unspent at that height. So I take a full node and I sync it to, let's say, 800,000th block. Okay, 800,000th block. And then in that hints file, I keep on adding UTXOs. Every time a new UTXO is created, I add it to that hints file. And every time that UTXO is destroyed and a new UTXO is created in its place, I remove that UTXO and then add the newly created UTXO. By the time I reach the active chain tip, which we are assuming is 800,000th block, we will have only the UTXOs which are unspent. Right, all the UTXOs that were created historically and were destroyed or were spent will not be a part of that hints file. Right, so let's read this again. Before using SwiftSync, someone who has already synced their node to a recent block creates a hints file that indicates which transaction outputs will be in the UTXO set at that block, i.e. which outputs will be unspent. This can be efficiently encoded to a few hundred megabytes for the current UTXO set size. The hints file also indicates what block it was generated at. We'll call the terminal SwiftSync block. All right. So the terminal SwiftSync block is the last block till which the hints file has been synced, and the hints file will contain all the unspent transaction outputs uh, till the terminal SwiftSync block, not the historic UTXOs. The UTXOs that were destroyed, that were spent, will not be a part of it. Only the UTXOs that are eligible to be spent at that given block height will be a part of that hints file. The user performing SwiftSync downloads the hints file and uses it when processing each block prior to the terminal SwiftSync block to only store outputs in the UTXO database if the hints file indicates that the output will remain in the UTXO set when the terminal SwiftSync block is reached, right? So when you are performing an IBD, when a Bitcoin node that deploys SwiftSync is performing IBD, it'll refer to that hints file, which has been created by some other node, right? Some other node. Let's say there's a developer who has the full node that is in sync with the active chain tip, and they've created a hints file, right? And they sign that hints file, and let's say they host it somewhere on their website, or maybe they hard code it in one of the clients, right? And it's very common. Like we have the hard coded data where developers sign that data and they make their public keys private, such as people can verify. We have these checkpoints in Bitcoin core as well, and there's a lot of data that's hard coded, and that data is signed by developers, right? So let's assume that there is somebody who has a full node. They've synced that full node in the active chain tip, and they have created a hints file that contains only the unspent transaction outputs at that block height, right? Which we are referring to here as the terminal SwiftSync block. Okay, and they upload it wherever, from where people can access it. Now if you are spinning up, if you're bootstrapping a Bitcoin node that deploys SwiftSync, then you refer to this hints file. What do you do? Every single time you are validating a transaction, you see that the UTXO that the transaction creates, is it a part of the hints file? If it's not a part of the hints file, then you do not add it to your UTXO set, because you know over a period of time that UTXO is going to be destroyed. So let's say UTXO was created in block 1, but then it was spent in block 2. So it's destroyed. Currently, it's not a part of the UTXO set, right? It's not a part of the UTXO set at what we are referring to as the terminal SwiftSync block. So you will not add it to your UTXO set in the first place, right? So that reduces your computational power exponentially, because you don't have to validate and add all the unspent transaction outputs to your UTXO set and then remove them, and then add them again, and then remove them, right? You directly just look into the hints file and see if this UTXO that is in block 1 or 100 or 200 or 500, is this still in the UTXO set at block 800,000, right? And if it's not there, then you don't validate that UTXO and you don't put it into a UTXO set, thereby reducing the computational time while performing an IVD. The user performing SwiftSync downloads the hints file and uses it when processing each block prior to the terminal SwiftSync block to only store outputs in the UTXO database if the hints file indicates that the output will remain in the UTXO set when the terminal SwiftSync block is reached. This massively reduces the number of entries that are added and then later removed from the UTXO database using IBD, right? Because you don't have to add those UTXOs that have been destroyed historically. You only add those UTXOs which are relevant at this point in time at the active change tip. So the hints file is every created output stored in the added to a crypto, right? So what do you do? Basically, there are two types of UTXOs, right? One are UTXOs. When you are performing an IBD, you come across two types of UTXOs. The first type is of those UTXOs which were created and never destroyed. They are still a part of the UTXO set at the active chain tip. Second are those type of UTXOs which were created and destroyed over due course, right? And they are not actively available in the UTXO set at the active chain tip, right? So those UTXOs which are a part of the active chain tip, which are still relevant, you add them to your UTXO set. And those which are not, what do? You add them to a database which is known as cryptographic accumulator. Now, every spent output is removed from the accumulator when the node reaches the terminal SwiftSync block. It ensures the accumulator is empty. Okay, let's read this again. To ensure that the hints file is correct, every created output not stored in the UTXO database is added to a cryptographic accumulator. Every spent output is removed from the accumulator, right? So you add it initially to the accumulator, right? And when it is spent, when it is destroyed, you remove it from the accumulator, right? So you add it to the accumulator first, and then when it's destroyed over due course of history, you remove it from the accumulator. When the node reaches the terminal SwiftSync block, it ensures the accumulator is empty, meaning every output seen was later spent, right? So every single output that is not a part of the hints file, when you come across it, you add it to a cryptographic accumulator. And later on, when it was spent or it was destroyed, then at that point in time, you remove it from the cryptographic accumulator, ensuring that when you reach the active chain tip or when you reach the terminal SwiftSync block, the cryptographic accumulator is empty, which ensures that every single transaction that was created, or every single UTXO that was created historically and got destroyed later on, was added to the cryptographic accumulator and has been successfully removed from the cryptographic accumulator, and they are not a part of your UTXO database, right? So you bifurcate the UTXOs into these two fractions. One is the UTXO set, which is relevant, which contains all the UTXOs that were created historically and were never spent. The second is a data structure called a cryptographic accumulator, where you add the UTXOs which were created historically and destroyed over a period of time, such that when you reach the active chain tip or you reach the terminal SwiftSync block, the cryptographic accumulator is empty, ensuring that every UTXO that was created or was recorded in the cryptographic accumulator was destroyed historically, right? If that fails, if that doesn't happen, it means that the hints file was incorrect and that IBD needs to be performed again from scratch without using SwiftSync, right? So if you reach the terminal SwiftSync block and even after that you have UTXOs in your cryptographic accumulator, it means that the hints file that you are referring to is malicious. You can maybe refer to somebody else's hints file, like maybe multiple developers might upload their hints file. So you can refer to somebody else's hints file, or you can just switch back to the regular IBD and be more perseverant and patient and invest five times more or 5x more the amount of time that it takes for IBD. And this way, users do not need to trust the creator of the hints file. A malicious file cannot result in an incorrect UTXO state. It can only waste a few hours of the user's computing resources. An additional property of SwiftSync that has not yet been implemented is allowing parallel validation of blocks during IBD. This is possible because AssumeValid does not check the scripts of older blocks. Entries are never removed from the UTXO database prior to the terminal SwiftSync block, and the accumulator used only tracks the net effect of outputs being added, created, and removed spent. That eliminates any dependencies between blocks before the terminal SwiftSync block. Parallel validation during IBD is also a feature of UTXO for some of the same reasons. So I believe this basically this process uh, it synchronizes or it works in tandem with assume UTXO and assume valid. Now, what's assume UTXO? Assume UTXO is basically, let's just understand what assume UTXO is. It's basically, you take a snapshot of the current UTXO set. Like I discussed recently that we had checkpoints in Bitcoin, right? We had checkpoints. We don't refer to them anymore, but we had checkpoints historically, right? Which are hard coded values, which are the hashes of the block headers, right? So what happens is that even right now, if you go to the code base of Bitcoin Core, you will find these checkpoints, right? So what developers over a period of time have done is that they've created checkpoints. Let's say the first checkpoint is at block 1,000. Okay, so what they'll do is they'll take the hash of the block header of block 1,000, and they'll hard code it, and they'll put it in the code base. When your node is validating transactions and blocks, okay, it'll validate block 1, 2, 3, 4, 5. When it reaches to block 1,000, it will check the hash of the block. If that hash matches with the hard coded value in the code base, then it means you're syncing with the right chain, right? And if it does not match, it means that you're syncing with the wrong chain. So these were checkpoints. Now we have this concept of AssumeUTXO, where uh, the snapshot of the latest UTXO set is referred to, right? So you use the snapshot of the latest UTXO set, and what that does is that if you connect your Bitcoin node with a Bitcoin wallet, it facilitates transactions immediately, right? So let's say I want to run a Bitcoin node. I bootstrap a Bitcoin node, right? Right now, my Bitcoin node is not aware of Bitcoin's blockchain's history. It is yet to sync from Genesis block to the active chain tip, but I want to use it right now. I want to connect my node with my Bitcoin wallet, and I want to start receiving and sending payments. I don't want to wait for 41 hours or 2 days or 4 days or 5 days. In that situation, what I can do is I can use Assume UTXO, right? Meaning that somebody, some developer or a group of trusted developers have validated the entire UTXO set, right? They've hashed that UTXO set and they've signed that UTXO set and they've made it available, right? You take that UTXO set, you refer to that UTXO set, and you use that UTXO set for sending and receiving payments. So if your Bitcoin node is connected to a Bitcoin wallet and you're receiving a payment, you will check, because right now it's not synced with the active chain tip, right? So you will refer to the snapshot of that UTXO set, and if that UTXO, if the transaction that you are receiving is a valid transaction, meaning it has the UTXO which is a part of that UTXO snapshot which you're referring to, then you can accept that payment or you can send that payments. And in the background, IBD will keep on happening. So you don't have to wait for the entire IBD to complete for you to send or receive transactions. You can immediately start sending and receiving transactions by quote unquote trusting somebody else who has validated the UTXO set and made it available for you. And in the meantime, you are doing the IBD in the background. That's what Assume UTXO is. Let's just read this. SwiftSync is a proposed mode for bootstrapping mutual nodes that allow them to postpone verifying all blockchain history until after the user is able to receive recent transactions, right? So basically, that allows them to postpone verifying all blockchain history until after the user is able to receive recent transactions, right? So you don't have to wait till you verify the entire blockchain to send and receive transactions, because this is usually what happens, right? If you are bootstrapping a Bitcoin node, it will not allow you to send transactions, it will not allow you to receive transactions till you have downloaded and validated the entire blockchain history, right? If it's a full node. But with Assume UTXO, so what you can do is the background, the IBD happens in parallel in the background. You have a snapshot of a UTXO set, and you can start receiving and sending payments instantaneously while the IBD happens in the background. How does this happen? Embedded in the code of the node would be a hash of the set of all spendable bitcoins and the conditions necessary to spend them. The UTXO set as of a certain recent point in time, right? So uh, let's say that the latest version of Bitcoin Core, it has it has hard coded the snapshot, meaning the hash of all the unspent transaction outputs, all the valid unspent transaction outputs, and till block height 800,000, right? So till block height 800,000, in our example, if there is a UTXO that was valid up till that point in time, you can send and receive that transaction immediately without having to download and validate the entire blockchain. After that, you have to validate, right? 800,000 onwards, you'll have to validate. So whenever, let's say, if 6 months ago Bitcoin Core's latest version was launched, then maybe the previous 6 months blockchain history you'll have to download and validate, and then after that you can use that UTXO snapshot, and then the IBD will keep on happening in the background. You don't have to wait for the IBD to get completed. You can start sending and receiving payments. Similar to the existing assume valid setting and other parameters used by nodes to converge on consensus, the revisions of the assume UTXO hash would be checked for correctness by developers during code review. This would allow operators of new nodes to optionally trust the hash and download a UTXO set that matches that hash, right? So there's trust involved in it, right? Every single time you refer to a hard-coded value without validating it, there is a level of trust involved in it. Even if you're referring to the checkpoints which are hard-coded, there is a level of trust involved in it. Even if you are bootstrapping a node and you refer to the hard-coded nodes to obtain addresses, then there is a level of trust involved in it. Even if you're using AssumeUTXO, there's a level of trust involved in it. Even if you're referring to we say assume valid, there's a level of trust involved in it. If you're referring to SwiftSync, the proposal that we are talking about, there's a level of trust involved in it because somebody else has done the validation, right? And they have validated that piece of data and made it available for you, and you are trusting them because at this point in time, you are not competent enough to validate that information yourself. So you are validating that information in the background, but till you validate that information, you are trusting that person or the information that they've provided, right? So you have not validated the entire UTXO set. You're trusting somebody else who's validated the UTXO set on your behalf. All right. So this would allow operators of new nodes to optionally trust that hash and download a UTXO set that matches that hash. For blocks produced subsequently to the UTXO set hash, the node would verify new blocks and update their own UTXO set like any other node without further trust, right? So as I said, let's say 6 months ago, Bitcoin Core's latest version was released, okay, and it has encoded the hash of the UTXO set till block 800,000. Now, in the past 6 months, let's say 1,000 more blocks have been mined, right? So those 1,000 blocks you will have to manually validate, right? You will have to validate those 1,000 blocks. For the first 800,000 blocks, you can just refer to the hard-coded value, and then whatever blocks have been mined post that, you have to manually validate those blocks, and then you have the entire UTXO set till the active chain tip, and then in background, then you go back to the Genesis block and you start validating. As currently designed, the node would also download and verify older blocks in the background so that it could eventually prove that the hash it first started with was correct. As currently designed, the node would also download and verify older blocks in the background, right? So the node will not only rely on this hash of the UTXO set, right? For the time being, because the node does not have the historic data and the node wants to start receiving and sending payments instantaneously, the node will temporarily rely on this hash. But in the background, what will the node do? It will download and verify older blocks. So node will start from the Genesis block and verify older blocks in the background so that it could eventually prove that the hash it first started with was correct, right? So the node will validate. The node will initially take the hash of the UTXO set that is hard coded, but at the same time, the node will start validating from block one. And when the node reaches the active chain tip, then the node will tally both of those hashes and the hashes match. Then the node will be certain that the UTXO set that it was referring to is correct, right? So what added advantage does assume UTXO give us? All right, it's not that it prevents you from doing the IBD. No, you still do IBD, but you don't have to wait for the completion of IBD to send and receive transactions. You can connect your Bitcoin node with your Bitcoin wallet and immediately start sending and receiving transactions. Whereas in the background, the IBD will happen. It might take 41 hours, 2 days, 3 days, 8 days, 1 month, depending on your bandwidth and the specifications of your computer or your node. But you don't have to wait for the IBD to be completed. Rather, you can spin up, bootstrap a node from scratch, and within no time, your node will be able to connect to your wallet and start sending and receiving payments. That's what Assume UTXO is. Let's see what Assume Valid is. Then we'll be able to link all these three: SwiftSync, Assume Valid, and Assume UTXO, and how they impact the initial block download. Is it too big? Should we read it? Let's see. So it's Assume Valid, basically. Wondering whether we should read it or just understand it. Not that big. Let's read it. Bitcoin 0.3.2 introduced a mechanism called checkpoints to prevent denial of service attacks during IBD by ensuring that new full nodes could be tricked into spending excessive amount of effort validating alternative blockchains that were different than the best known chain at certain points in time, right? So this talks about checkpoints, and we've discussed checkpoints in detail in the preceding sessions. So let's not go into that. I'm assuming everybody knows what a checkpoint is. And if you don't, then you can look up on the internet. You'll find what a checkpoint is in terms of Bitcoin's initial block download. Bitcoin 0.5.0 built upon those checkpoints to speed up IBD by skipping verification of signatures in blocks that were earlier in the blockchain than the most recent checkpoint. Over time, other improvements in Bitcoin Core security, such as headers first sync and minimum chain work, have reduced the need for checkpoints, while at the same time, many Bitcoin developers have expressed the desire to remove checkpoints because they confuse new developers about the security model. Checkpoints make it look like Bitcoin developers are deciding which chain is valid, even though the intent was always to only accept the chain which the software had already decided was valid, right? So currently, if you're syncing a Bitcoin block, right, we deploy this mechanism headers first thing. Initially, what used to happen is that nodes, you used to validate the entire block, right? Now, if you, let's say the first checkpoint is a 1,000 block, you validate 999 blocks, then you reach the 1,000th block, and then you realize that you're syncing to the wrong chain because the hash of the header of the 1,000th block of the chain that you are syncing with is not matching with the hash of the 1,000th header of Bitcoin's mainnet, which is hard coded in whatever client that you're using, right? So that was like wasting a lot of computational resources. So then this process was incorporated known as headers first sync. So what a Bitcoin nodes now do is that they sync the headers first. So they'll sync the headers to the active chain tip. And once they've done that, they know that they are connected to the right chain. After that, they'll validate the entire block. So the Bitcoin nodes now do not validate the entire block. They first validate the headers of all the blocks of the entire blockchain from the Genesis block to the active chain tip. And then they're sure that they are syncing the right chain. After that, they come back and then start downloading the blocks and minimum chain work. Like initially, we used to refer to the highest chain. So if your node is aware of two chains, then the chain that had the higher block height would be referred to as the correct chain by a node, but that was later on changed. And currently, the chain with the higher proof of work is referred to as the correct chain, right? So these are some things that kind of did you know or trivia's. When we're talking about IBD, what's a headers first thing, what's minimum chain work, what's assume UTXO, what's assume valid. We know what's minimum chain work now. We know what's headers first thing now. We know what's assume UTXO now. Now we know what's assume valid. Assume valid blocks is a new feature that separates the signature skipping optimization from the checkpoints anti-denial of service mechanism. So they can each be dealt with independently. Assume valid block is a block that individual valid blockchain, readable determinist is compatible Bitcoin blockchain, including the Bitcoin question block or any. If someone knows a full node for the first knows about any blocks, they can then provide the highest height of they can then provide the highest height Bitcoin core 0.14.0 and the software in the assume valid signatures consumes a lot of CPU during IBD. Using assume valid blocks can significantly speed up IBD. All blocks assumed valid Bitcoin transaction, the most computationally intensive amount of time and computational power as compared to validating any other or performing any other validation checks on a Bitcoin transaction, right? What assume valid does is right is that there is somebody, there might be a developer or a group of developers that will validate all the blocks up till block height X, right? And they'll make that data available in public. When you are syncing your block from Genesis, your node from Genesis block to the active chain tip, you will refer to that assume valid block index that is shared by other developers, and you will skip the signature verification till there, right? So let's say that somebody else has validated all the blocks up till block number 8,000 and they've made that data available. You will refer to that data which is made available by them, and you will assume that all the digital signatures up till that block height are valid. You will not validate those digital signatures. You'll just assume that those digital signatures are valid because there are a lot of people that have validated that data over a period of time. Hundreds and thousands of people have validated that data over a period of time, and it's public information now. It's common knowledge. So there's no need for you to manually validate and verify each and every signature. You skip the signature verification part, right, which is the most computationally intensive part of validating a Bitcoin transaction. That's what assume valid is. What is assume UTXO? You take the snapshot of a UTXO set, right? And you assume that all the UTXOs in that UTXO set are valid, and you start accepting payments and sending payments. And in the background, you'll keep on performing the IBD. What's assume valid? You'll assume that all the digital signatures up till a certain block height are valid, and you skip the signature verification, which is the most computationally intensive part of the IBD, right? So these are some mechanisms basically that reduce the time of IBD. If you are bootstrapping a Bitcoin node and you set assume valid as true, you set assume UTXO as true, then your node can initially start sending and receiving payments. It'll skip signature validation, and if you are also incorporating SwiftSync that we just talked about, then in that case, you can sync all of these things together and get a speed of about 5.82x of about 5.82x, right? And how does SwiftSync work? We covered it recently. We just go through these two or three passages against paragraphs against, which summarizes what SwiftSync is before we move on to the PR review. It's 8:45 because already. So before using SwiftSync, someone who has already synced their node to a recent block creates a hints file, right? That indicates which transaction outputs will be in the UTXO set at that block, i.e. which outputs will be unspent. This can be efficiently encoded to a few hundred megabytes for the current UTXO set size. The hints file also indicates what block it was generated at, which we'll call the terminal SwiftSync block, right? So currently the UTXO set is a few hundred megabytes. The user performing SwiftSync downloads the hints file and uses it when processing each block prior to the terminal SwiftSync block to only store outputs in the UTXO database if the hints file indicates that the output will remain in the UTXO set when the terminal SwiftSync block is reached, right? So when your node is performing IBD, it will only take that UTXOs and put it in the UTXO set, right? It'll take only those UTXOs and put it in the UTXO set, which it knows will be active, which have not been spent historically. This massively reduces the number of entries that are added and then later removed from the UTXO database during IBD, right? This can be done parallelly as well. This can be done parallelly as well. Even if you're using assume valid or you're using assume UTXO, when the parallel block download is happening, when the parallel IBD is happening, you can deploy the Swift sync process. That's how all these three mechanisms like work together. To ensure that the hints file is correct, every created output not stored in the UTXO database is added to a cryptographic accumulator. Every spent output is removed from the accumulator. When the node reaches the terminal SwiftSync block, it ensures the accumulator is empty, meaning every output seen was later spent, right? So every single time you come across a UTXO, you add it to the cryptographic accumulator, which is not a part of the hints file. And then when it was spent, you remove it from the cryptographic accumulator. And then when you reach the terminal SwiftSync block, if your cryptographic accumulator is empty, it means that all the valid UTXOs are in the UTXO database, i.e. the hints file, and all the spent UTXOs, meaning those UTXOs which were destroyed historically, have been removed from the database. And if that doesn't happen, then you're probably syncing to or referring to a malicious hints file. Then you can just go back to the legacy or the default way of IBD. So that's what this proposal is all about and how it hastens the IBD process. It was a little lengthy because I saw a few new faces, so I thought we should talk about assume valid and assume UTXO and not assume that people already know that. So we tried touching upon what assume valid is, what assume UTXO is, what Swift sync is, and what checkpoints are, what pre-sync headers are, and how all of these proposals and developments come together to hasten and speed up the initial block download. So if anybody has any questions, anything to share, any experiences while syncing their block, any glitch ups or any hiccups they came across, then please feel free to unmute yourself and share if you have anything to say. I'll just
Yeah,
pause 30
yeah,
seconds. Yeah.
I wanted to ask why is it more efficient to add and remove from the cryptographic accumulator? Why is it faster than just keeping all the UTXO in some cryptographic accumulator, and then in the end you will finish only with the UTXOs that weren't unspent along the way?
Right. So this is just a mechanism of cross-checking, right? So you have two data structures. One is your UTXO set, right? Which has all the UTXOs which are unspent till the active chain tip, right? But there were also UTXOs that were created historically. There were UTXOs that were created historically and they were destroyed as well. To ensure that your UTXO set does not include those UTXOs which were created historically and destroyed later, you store them in another database, which is cryptographic accumulator, right? So you have two databases. One is a UTXO set in which you only put those UTXOs which have never been spent. And the second is a cryptographic accumulator in which you put those UTXOs which were created historically, but they were spent, right? Now you need to cross check whether they were certainly spent. And how do you do that? By adding them to a cryptographic accumulator when they were created and removing them from the cryptographic accumulator when they were spent. And by the time you reach the active chain tip, if your cryptographic accumulator is empty, it means you have successfully removed all the UTXOs that were created historically and destroyed, and thereby ensuring that none of those UTXOs that were destroyed or spent are included in your database of your UTXO set. They were put in the cryptographic accumulator and they were destroyed and they were never a part of your UTXO set.
Yeah, I understand why it works. I just don't understand why it makes everything much more faster.
So basically, it how it makes the thing faster is that you don't add those UTXOs to your UTXO set, right? So basically, if you are doing an IBD, every single time, like this, let's assume there's a genesis block, right? So you will take all the UTXOs from the genesis block, you will validate them, you'll put them to the UTXO set, right? And then in the second block, in the third block, in the fourth block, right? But right now, what your node will do is it will not take those UTXO sets, those UTXOs, and put it to a UTXO database in the first place. The moment it knows that a UTXO was created, however, it was destroyed historically, it will not put it in your UTXO database in the first place. It will only look for those UTXOs which were created but they were never spent, and it will validate those UTXOs and it put those UTXOs into your UTXO database. So you don't have to validate all the UTXOs that were created historically. Rather, you only validate those UTXOs which were created historically and were never destroyed. So that reduces your work exponentially.
Yeah, so you don't, it's less write operations because the UTXOs that are not spent are already in the database, and you need to write and delete only the UTXOs that are spent through the cryptographic accumulator.
Right. So it saves your time. You don't have to validate all the UTXOs and put them in your UTXO set and then remove them. You only put the UTXOs that have never been unspent. And the spent ones, you put them in the cryptographic accumulator.
Okay.
Right? Great. Okay. We will move on to the Bitcoin Core PR review. How much time do we have? We have approximately 10 minutes, so not take more than that of your time. We'll just read this. Obviously, we can't dig into the code because time won't permit us to do that, but we just read it. It's something interesting. So those of you who are familiar, uh, I mean, I'm sure most of you know that Bitcoin Core has an inbuilt wallet, right? Like most people, like the Moon wallet and this wallet and that wallet, and these are very popular wallets, right? Blue wallet, but Bitcoin Core also has an inbuilt wallet, and initially people were using that wallet, like during the days of infancy of Bitcoin, people were using that wallet, but later on, like wallet technology became a completely different faculty, an independent faculty that people started referring to, and then much more advanced wallets came into place, and I believe there are very few people today who use Bitcoin Core's default wallet. Most people connect their nodes with an external wallet. Nevertheless, Bitcoin Core does have its own wallet, and it because it has its own wallet, it has a fee estimation mechanism as well, right? So if any of you have used this popular website known as mempool.space, you see that it has the fee estimator. It has a fee estimator, right? It predicts the fee market. So like that, Bitcoin Core's wallet also has a fee estimator and it predicts fee, right? So if you want to send a transaction, it will estimate a fee for you depending on various parameters, right? If it's of high priority, if it's of low priority, if it's of medium priority, based on all of these factors, it will estimate, right? And you have to give it a target. So you have to let your node know which transaction you intend to broadcast, and also let your node know how many blocks you want that transaction to get confirmed in, right? So if you want your block to get if you want your transaction to get confirmed in 10 blocks, you have to specify that. Based on that, the node will calculate a fee and let you know. If you are okay to wait for 20 blocks, then the fee might be less. If you want it to get confirmed, for instance, in 5 blocks, 3 blocks, the fee will be high. So depending on how quickly you want your transaction to get confirmed, you have to give a confirmation target, and based on that, using its fee estimation algorithm, Bitcoin Core's wallet will calculate a fee and let you know what that fee is, right? Up till now, the mechanism, there are basically different algorithms as well to do that. Up till now, what was happening is that Bitcoin Core used to refer to confirmed transactions only, right? How Bitcoin Core estimated the fee is that, in a very generic way, your node would keep track of when it sees a transaction for the first time. That's when it reaches its mempool, right? So when your node saw a transaction for the first time, right, beginning from there, when the transaction got confirmed into a block, how much time did it take and how much fee was paid, right? So let's say I broadcasted a transaction. My node saw that transaction for the first time at time X, and then that transaction got confirmed, let's say after 6 blocks. And the amount of fee that I paid is 10 sats, right? So it will take all of these parameters. A, the time at which your node saw the transaction for the first time. B, how much time did it take for the transaction to get confirmed. See how much fee was paid, and depending on these factors, uh, the transaction will be put. I mean, buckets are made, and using all these parameters, transactions are put into buckets. So next time whenever your node sees a transaction which has all the similar attributes, let's say same size and the same confirmation target, it will suggest the same fee. If the congestion is same, it will suggest the same fee, because historically it will observe that the similar transaction that was broadcasted some time ago paid, let's say, 10 sats per virtual byte and took 6 blocks to get confirmed. So if you are now broadcasting a similar transaction and the congestion of the mempool is the same, and you are willing to wait for 6 blocks, then it will suggest a similar fee to you, right? So that is how broadly Bitcoin Core's estimation fee estimation works. And for that, it only refers to confirmed transactions. It doesn't refer to unconfirmed transactions. It will only use confirmed transactions as a parameter, right? But this proposal, what this does is that it adds another dimension that you can also forecast the fee based on mempool. Up till now, the mempool was not taken into consideration for fee estimation. Only confirmed transactions were taken as a parameter, right? So when you ask Bitcoin Core for to estimate a fee for yourself, it will see your transaction and then it will compare it with the confirmed transactions, right? It will compare it with confirmed transactions, and based on confirmed transactions, it'll estimate a fee. It'll never look at unconfirmed transactions that are in the mempool. However, there are some drawbacks of this. What drawbacks? One drawback is that when you are talking about confirmed transactions, your fee estimation will not instantaneously adjust to the dynamically varying fee market, right? The fee market keeps varying dynamically. Like every minute, the fee market might change, right? The mempool might change every minute, right? The mempool is not static. So if any of you have created your own blocks, if any of you are a home miner, and if you use something like Datum or Stratum V2 to create your own templates, and you look at the logs, you'll see that your node creates a new template every second. Every second your node might create a new template, right? So your mempool keeps on changing every second. It sees new transaction, it rejects new transactions, right? So your mempool keeps on changing every second. But as for the confirmed transactions are concerned, then the state of the blockchain changes when once every 10 minutes, right? Roughly once every 10 minutes. The state of your mempool changes every second, but the state of the blockchain changes roughly once every 10 minutes. So what happens is that when you are referring to only confirmed transactions, uh, confirmed your fee estimation will not instantaneously adjust to the dynamically varying fee market, right? Because the information that your fee estimation algorithm has is updated every 10 minutes. But if you're referring to the transactions in the mempool, then the information that your fee estimator has is it is updated every second, right? So you can give more accurate and more instantaneous estimations, right? So this is the proposal, which up till now Bitcoin Core would only refer to confirmed transactions and use them as a parameter to estimate fee. But now this proposal suggests that Bitcoin Core should add another dimension, which is giving a fee estimation based on the mempool, because that's the mempool varies like every second, so it has more recent information and can give more accurate prediction, right? So let's just read through what this is, and I don't think we'll have time for to dig into the code, but we'll read through this. So what's the motivation and background of this PR? The current fee estimator in Bitcoin Core used by the wallet and exposed to clients via, I'll not highlight it because it's hardly visible. The background is black, so when I'm highlighting it, the text is not visible. I just move the cursor from under the text that I'm reading. The current fee estimator in Bitcoin Core used by the wallet and exposed to clients via RPC is multi-block policy estimator, right? This is a class in Bitcoin Core that is responsible for uh, uh, basically that has the code that is responsible for estimating fee. This estimator maintains a vector of fee rate buckets ranging from 1000 sats per KVB, meaning 1 sat per virtual byte. That's the minimum relay fee for Bitcoin Core, to 10,000 sats per virtual bytes, right? But these buckets are spaced exponentially by a factor of 1.05. So as I mentioned that what Bitcoin Core does is that it creates buckets of transactions, right? Buckets of transactions that will require similar fee to get confirmed, right? And it uses those buckets. So when you broadcast a transaction and you ask Bitcoin Core to estimate a fee, it tallies it sees which bucket that transaction fits into based on a number of parameters, based on the confirmation target, based on the size of the transaction, right? It'll see which bucket it fits into, and it'll give you the fee estimation of that bucket, right? Now these buckets are spaced exponentially by a factor of 1.05. For example, if the first bucket is of 1000 sats per kilo virtual byte, that's 1 sat per virtual byte, right? So if you broadcast a transaction and it fits into the bucket which has transactions of 1 sat per virtual byte, then Bitcoin Core will give you a fee estimation of 1 sat per virtual byte, right? And there are multiple buckets, and those buckets vary in linear proportion of 1.05, right? So if the first bucket contains the transactions of 1 sat per virtual byte, the next one would be 1.05 sats per virtual byte, and so on. The estimator works by tracking each transaction's fee rate and assigning it to the appropriate bucket, monitoring transactions as they leave the mempool. If a transaction is confirmed in a block, the estimator records success in the bucket along with the number of blocks it took to confirm, i.e., the difference between the confirmation block height and the height at which it was first seen in the mempool, right? So, what was the block height when the transaction was first seen by your node? And what was the block height when the transaction got confirmed? So that's a confirmation target, right? So if your node saw a transaction for the first time when the block height was 1000, and the transaction got confirmed when the block height was 1006, so the confirmation target was 6, right? The confirmation target was 6. So it'll use that as a parameter that it took 6 blocks for this transaction to get confirmed at 1 sat per virtual byte. So next time when you broadcast a transaction, which is let's say of the same size, and the confirmation target is also 6 blocks, it'll tell you that hey, it'll fit into the bucket of 1 sat per virtual byte, and it'll suggest you a fee of 1 sat per virtual byte. If a transaction is removed for any reason other than inclusion in the block, it is recorded as a failure, right? This data, so basically, if a transaction is removed from your mempool and it is not confirmed in a block as well, then it is recorded as a failed transaction for whatever reason. This data is aggregated using an exponentially decaying moving average. So old data points become less relevant over time, right? So basically, you don't want to refer to transactions that are very old, right? So if a transaction is, let's say, 5,000 block old, you will not use that as a parameter, right? That even though that's a confirmed transaction, but it's obvious that 5,000 block ago, the fee market was completely different. Today, the fee market is completely different. So it'll only use recently confirmed transactions as parameters. A knife fee rate estimator by a knife fee rate estimate by this estimator would provide an estimate for a confirmation target n by going through these buckets from the lowest bucket to the highest bucket, returning to the lowest fee rate bucket, where more than 80% of the transaction first seen within these n blocks were confirmed, right? So it'll first see if the transaction fits into the lowest bucket, which is 1 sat per virtual byte, because obviously you want people to pay as less fee as possible. So you'll see if it's possible to get this transaction confirmed within the confirmation target by paying 1 sat per virtual byte. If no, then it'll see if this transaction fits at 1.05 sat per virtual byte, so on and so forth. And then eventually it'll fit it into the appropriate bucket. However, the fee estimator is more complex than this. It maintains 3 sets of these buckets: short term, medium term, long term, right? So depending on each decaying at a different rate, right? So short term, medium term, long term is basically short term is very recent confirmed transactions. Medium term is a little more than that. Long term is a little more than the medium one. These allow the estimator to provide fee estimates in two modes: conservative, right? So the fee estimator, Bitcoin Core's fee estimator provides fee estimates in two modes: conservative, uses long-term data for more cautious estimates, and is tailored towards users who do not plan to not fee bump. These fee rates tend to be higher, right? Because the more data that you analyze, the more chances are that your fee prediction will be accurate, right? Because in the short term, you might see you might see an exponential spike in the fee rate, or you might see that the fee rate went down extremely low during a small time horizon. But over a long time horizon, the volatility kind of flattens, right? So if you want a more conservative approach, then you use the long-term parameter. Then you use this long-term fee rate estimation, right? Which in which you might end up overpaying a little, but you'll be sure that your transaction will get confirmed within the confirmation target. And then economical one relies on more recent short-term data, right? So in this case, you'll probably the fee estimator will give you a cheaper fee, but there is also a possibility that your transaction might not get confirmed if there's a spike in the fee rate exponentially within a short period of time. So the key advantage, this approach is highly resistant to manipulation because all transactions must be. So what's the advantage of the current approach where we only refer to the confirmed transactions? It is relayed, ensuring visibility to miners, confirmed, ensuring they follow consensus. Sorry. Yeah, this approach is highly resistant to manipulation because all the transactions must be relayed, right? So when you are referring only to confirmed transactions, you have to be sure that these transactions have been relayed to the entire network and they've been validated by the entire network, right? Because a transaction cannot be confirmed in the blockchain unless and until it is relayed to the network and it is validated by the network, right? So you're sure that the information that you're referring to is foolproof. However, when you are referring to the mempool, it's possible that the transaction might be an out-of-band transaction, which is not related to the network, and maybe it's a non-standard transaction, right? And also, it's not a confirmed transaction. So mempool unaware. Key limitations for users, mempool unaware. Does not consider the current mempool unconfirmed transactions when estimating fee. As a result, it remains oblivious to certain changes, right? So in the contemporary mechanism of fee estimation in Bitcoin Core, since it does not refer to the unconfirmed transactions in mempool, it is not aware of the latest evolutions happening in the mempool. Rather, it refers to only confirmed data. And that is why the information that it is aware of changes only once every 10 minutes. Package unaware only considers individual transactions. So currently what happens is that Bitcoin Core's fee estimation estimates the fee for each transaction individually. So if there is a package of a child and a parent, it will not consider that package and estimate a fee for the entire package. It will only estimate the fee for individual transactions. And we know that now there is a possibility of something referred to as an ephemeral anchor, which is a zero fee output basically. So if you are analyzing each transaction individually, then this transaction, an ephemeral anchor will never get broadcast because it's not paying any fee. You have to analyze it with a package, with a V3 child pays for parent package. Only then will you be able to broadcast that transaction, right? So this new proposal with PR, what it does is it proposes that fee estimation should also be allowed to be made based on mempool. For what reasons? For primary, one reason is that the mempool changes dynamically, and that is why your fee estimation algorithm has more latest and more updated information. Secondly, the conventional or the legacy mechanism of Bitcoin Core of estimating fee refers only to confirmed. Is analyzes each transaction individually, and the need of the hour with evolution of ephemeral anchors is that you need to analyze the package together in order to estimate a fee for it because ephemeral anchors are broadcasted without any fee. So if you analyze them individually, they'll never get broadcast, right? So broadly, that's what I wanted to cover. That what this PR does is that Bitcoin Core's conventional fee estimation mechanism only takes confirmed transactions as a parameter and uses them for fee estimation. But this proposal kind of expands its spectrum and also proposes that the unconfirmed transactions in the mempool should also be referred to because that gives a more updated and a more recent information of the fee market, and also it allows you to keep in sync with new evolutions like ephemeral anchors so that you don't have to individually analyze transactions and estimate fee for them. Rather, you can analyze the entire package and estimate the fee for the entire package. That's what this PR aims to achieve. Like anybody who has the time, the bandwidth, the perseverance, and the interest can read the entire documentation. It's going to take a lot of time, and can also go and dig into the code and also this chat history of the people that attended the PR review. And if you have any questions, any queries, feel free right now to unmute yourself and ask questions, or even later on post in Discord, and we'll be more than happy to help you to the best of our competence. I will stop sharing my screen right now. Uh, we covered the news article and we covered the PR review, and that is all that we had time for. There's something in the chat. Let me see what it is. Got to jump. No worries. Thanks, Faisal. No worries. Sorry, guys. Had to go. Maghrib. No worries. Right. Cool. So we have three guys. Any questions? Any observations? Anything anybody would like to share before we wind up the session? And if none, then thanks a lot, guys, for showing up for the session. Hope to see you guys next week. Good evening, good night, wherever you are. Enjoy your dinner.